Let's take a look at the mathematical operations on complex numbers. Can you calculate the result of these operations? Let's first begin with the addition of two complex numbers. Consider two complex numbers, Z1 equal to A plus IB and Z2 equal to C plus ID. The sum of these two complex numbers is equal to A plus C plus I multiplied by B plus D. What did you notice in this addition operation? The sum of the real parts of the two given complex numbers gives the real part of the resultant complex number. Similarly, the sum of their imaginary parts gives the imaginary part of the resultant complex number. The resultant number is also a complex number. Let's find the sum of the given complex numbers. The sum of the real parts of the complex number is 11, and the sum of the imaginary part of the complex numbers is 8. The resultant complex number is 11 plus 8i. Let's look at the properties of addition of complex numbers. The sum of two complex numbers is also a complex number. Therefore, we can say that complex numbers are closed under addition. The commutative property of addition states that two complex numbers can be added in any order. The associative property of addition of three complex numbers states that the numbers can be grouped in any order. 0 plus 0i, or 0, is called the additive identity of a complex number, because adding them results in the same complex number. For every complex number z, there exists a complex number minus z, called the additive inverse or negative of z, such that their sum is 0. Next, we'll find the difference of two complex numbers. Consider two complex numbers, z1 and z2. To subtract z2 from z1, first find the additive inverse of z2 and then add it to z1. This is the difference of the two complex numbers. Let's subtract 2 minus 7i from 3 plus 2i. The additive inverse of 2 minus 7i is minus 2 plus 7i. Therefore, the difference is 1 plus 9i. The difference is also a complex number. Next, we'll multiply two complex numbers. Consider two complex numbers, z1 and z2. The product of the complex numbers z1, z2 is equal to AC minus BD plus I multiplied by AD plus BC. Let's look at an example. Here we'll multiply 1 plus 4i by 3 plus 2i. On multiplication, we get minus 5 plus 14i. The product is also a complex number. Let's look at the properties of complex numbers under multiplication. On multiplying two complex numbers, the product is also a complex number. This means that complex numbers are closed under multiplication. The commutative property of multiplication states that two complex numbers can be multiplied in any order. The associative property of multiplication of three complex numbers states that the numbers can be grouped in any order. One plus 0i, or 1, is called the multiplicative identity of a complex number, because multiplying them results in the same complex number. For every complex number z, there exists a complex number 1 divided by z called the multiplicative inverse of z, such that their product is 1. For any three complex numbers, multiplication is distributive over addition. Let's again consider complex numbers z1 equal to a plus ib and z2 equal to c plus id, where z2 is not equal to 0. The quotient z1 divided by z2 can be obtained by multiplying z1 by the multiplicative inverse of z2. Now, we'll multiply the numerator and the denominator by c minus id to get a real number in the denominator. This process is called the rationalization of the denominator. We know that I squared is equal to minus 1. This is the required quotient, which is also a complex number. Let's divide 2 plus 5i by 1 plus 2i. The multiplicative inverse of 1 plus 2i is 1 divided by 1 plus 2i. Now, we'll multiply the numerator and the denominator by 1 minus 2i. We know that I squared is equal to minus 1. On simplifying, the quotient is equal to 1 divided by 5 multiplied by 12 plus I. Now, we'll learn to find the powers of I. You know that I squared is equal to minus 1. I cubed is equal to I squared multiplied by I, which is equal to minus I. I raised to the power 4 is equal to I square whole squared, which is equal to 1. I raised to the power 5 is equal to I. Similarly, I raised to the power 6 is equal to minus 1, and so on. I raised to the power minus 1 is equal to 1 divided by I. On multiplying the numerator and denominator by I, we get I divided by I squared. On simplification, we get minus I. I raised to the power minus 2 is equal to 1 divided by I squared, which is equal to minus 1. Similarly, I raised to the power minus 3 is calculated as I, and so on. What pattern did you notice here? For any integer k, I raised to the power 4k is equal to 1, I raised to the power 4k plus 1 is equal to I. I raised to the power 4k plus 2 is equal to minus 1. I raised to the power 4k plus 3 is equal to minus I. These results are more useful while simplifying expressions involving complex numbers.